In this video, we discuss another special case. This function uh, in the standard form of linear differential equation may not be continuous, but it's piecewise continuous. Now we want to solve, get a possible solution for this differential equation, right? So let's see that start from just work this out by example. We still can get a solution for this, right? One of the requirements is our function has to be continuous on the interval of existence, right? So our solution has to be continuous, dy over dx equal to, no, plus y equal to f of x, right? Where this is the initial condition, we know that y of 0 equal to 0. We also know that f of x is a piecewise defined function. So this is equal to 1 when x is between 0 and 1, and 0 when x is greater than 1. So this is very common in the setup of the differential equation, right? You are suppose you have a system, you are given some external force in the first 1 hour, constant force. After that, we don't do that anymore. So this is basically a piecewise function, piecewise continuous. On 0 to 1, always 1 continuous. On 1 to infinity is always 0 is continuous, right? So how do we solve this kind of differential equation is also very important, right? So there's really not much we can do, right? And you have to divide our divide the what's that called differential equation into different subcases based on the definition of f. So first on the interval from 0, 1, we get our function f is what is 1. So we get a differential equation dy over dx plus y equal to 1, right? Now we want to get our what's that called? Multiplying factor mu, right? So mu of x in this case is e to the power integration 1 dx, right? Just look at our standard form, you know that you notice p of x is actually 1 and f of x is also equal to 1. And so we are looking for one of the special functions. So this is just the e to x, right? And so we get multiplied by e to x on both sides of our equation, you get e to x times dy over dx plus e to x times y equal to e to x. So left side is d over dx, e to x, y. Right side is e to x, and take a derivative, you get e to x y equal to e to x plus a constant c, right? And so that y here is 1 plus c times e to negative x, right? And because we have an initial condition, which is y of 0 equal to 0, which happen to be in the first interval, right? We can figure out what is c here. So since y of 0 equal to 0, to get 0 equal to 1 plus c times e to 0. So which means c here is actually negative 1, right? So on the interval from 0 to 1, the solution is y equal to 1 minus c, and 1 minus e to negative x, right? So we get part of our solution now. Now let's go to the second half, right? The second half is on the interval from 1 to positive infinity. Now we have a different differential equation because f of x is different. So we get dy over dx equal to plus y equal to 0. In this case, our p of x is still 1, but f of x is basically 0, right? So we get our multiply factor, same thing, because p doesn't change. So mu of x is still e to x. You get e to x dy over dx plus e to x times y equal to 0. So you get d over d to dx, e to x y equal to 0, which means e to x y must be a constant. C you can call C1 here. So Y here is actually C1 times e to negative x. Now the question is, what is C1, right? So what is C1? And remember that our function has to be continuous, right? Our function has to be continuous. So on the first half of the function, y of 1 is 0, right? Y of 1 is, no, not 0, sorry. Y of 1 is 1 minus e to negative 1, right? So, so has to be continuous. We know that the function as x goes to 1 on the right side, the function y here, using this formula here, is c1 plugging 1, which is e to negative 1, right? And also we know that y of 1 equal to 1 minus e to negative 1. Well, this has to be same because that's basically the requirement for our function to be continuous. Right limit should equal to the function value, right? So we set up our equation, which is c1 e to negative 1 equal to 1 minus e to negative 1. So that c1 is actually e minus 1, right? Multiplied by e both sides. So we get our second piece, which is on the interval from 1 to infinity, which is y equal to e minus 1 times e to negative x. Now we have both pieces. One is from 0 to 1, the other one is from 1 to polar infinity. So we get our solution here. So the solution is y of x equal to two pieces. From 0 to 1, you get 1 minus e to negative x when x is from 0 to 1. When x is greater than 1, so this is e minus 1 times e to negative x. So that's basically the solution of the initial value problem we are starting from. So so this is basically deal with the function in the standard form of linear differential equation. The function on the right side is a piecewise defined function, two pieces. What you do is solving the differential equation on each piece and using the initial condition to fix one of the constant and using the continuity of the solution to fix the other constant. So in the end, you get a piecewise defined function for this given differential equation.